Let's go quickly to the decision analysis, to that summary report. This is probably, again, the best high-level look at all of the data wrapped up together. Hit the magnifying glass quickly here, and you can see going from baseline to base case, as you'd expect, there's no investment costs in our current as-is. This is supposed to be the as-is kind of current today situation. We do have an equivalent annual cost, and we see that some of this goes up. This is fairly common, that the price or the cost would go up between those scenarios, and many times that's related to the actual size increasing, going from, again here, 53 facilities up to 65, going up by a factor of about 50% in the total square footage, conditioned square footage. Many times older buildings that wouldn't have been air conditioned in the past, they now have new creature comforts and things like that added in as well. So sometimes that also has an impact on why you would see the costs, the energy and the cost go up between these scenarios. But then going forward, these three future scenarios, we see from the base case to the better case, a significant reduction in the energy usage. You're looking at the source energy, and a reduction in the equivalent annual cost. This, again, is going to be the summed up version of the capital cost for doing all the improvements and the energy related costs. So summing those together, the capital cost is going to be annualized the way you normally would for any economic analysis, and then added to that annual cost for energy. And we see another reduction here for the best case. You see these are relatively close. We don't always see a reduction at this level. You can kind of visualize in your mind the chart that I think Richard has shown quite a few times, where we start off at a higher cost, and then we'll see some drop down, usually to something we might call roughly a better case. There's some room. I mean, the easy way to speak about that is just to say we're not currently at the minimum cost point. There are things that can be done that would reduce our energy use and reduce our cost. And then many times we'd actually have to increase the annualized cost, put more and more investment in to further reduce the energy. And in this situation, it looks like, because of the either the cost related to it, and usually more than anything, the local utility rates determine how far down we can go and still be at a cost minimum. So it wouldn't have been surprising if this number went back up, maybe up to 12 million a year, or even up above the base case, to get further and further. If we continue to push these, it may go that way. But just kind of generally visualizing that curve that Richard showed a number of times. Okay, so now that we're at this point, again, I feel like this is where we can add a lot of value with a small amount of time. We can look at adding cogeneration to the plant and look at adding solar. I think we would normally, sometimes we do those in two separate scenarios. We could also mix them together, and we could do a final scenario that way. Since the best case is our lowest cost case, I'm going to do our tree off of that best case. Sometimes, again, depending on the scenario, you may want to branch it off the better case. And Richard's talked a little bit about this as well. It may make sense to put more money into your supply solutions rather than further reducing the loads on the building. Usually there's a distance you can go, and that's often the better case itself is kind of that situation where it's most cost effective to reduce the loads. And I think we're all kind of familiar with that. It's almost always better to start there. You wouldn't start by just throwing a bunch of solar on your building. But at some point, supply solutions can become more cost effective than further reduction within a building. There are some things that you can't potentially get much further, especially internal loads or heavily load dominated buildings. There may not be that much more you can do. So let's go ahead and do that. We're going to go back to the study information and to the alternatives, and I'm going to copy the best case. So one thing I like to do here, you can see the order. This is just a minor point. I'm going to go ahead and increase the order. This just makes sure that regardless of when we created the study or the alphabetical order or anything like that, that these stay in the order across with the mini tabs. So when I create our next one, we're going to say best case with let's go ahead and do Cogen first. Create the copy. And this is a pretty quick process considering it's copying over all the information that we've already done. And so we basically, right now, without making any changes, we have an exact copy of the base case. And I think because I didn't hit continue after I made these changes to the order, then it didn't save that. So I'll go ahead and do that again. And I'm starting at the bottom. Again, this is a small note. Richard made one of these, just a process-wise note 2 weeks ago. If I started upping the order up here, it would start moving these around as I went. So if you start at the bottom with your final one, it just makes it so you don't have to hop around and try to find whichever one you want to get to that final position. Let's go ahead and hit continue. Okay, so because it's an exact copy, all the simulations for the buildings, the optimization in the installation or subsection, all of that is already done. We're going to go through to this section and go to the equipment and measures. And once this loads up, we're going to go over to the best case and open up the ability for it to choose cogeneration equipment. And it's kind of strange language, but then we'll kind of talk a little bit about what this equipment list represents again. Usually I think it takes a couple times going over what does this really mean. So you'll see in this list, we can make it a little bit bigger here. Again, this is a list of technologies that could be considered for the cluster of buildings that we're currently looking at. So I'm looking at this best case scenario. I'm now in the centralized cluster. It was just the top one of the two that were in the list. And I can scan down through here and see that there are only a couple technologies that could exist in this solution. So the distributed chillers and most of the rest of these things. So when I say they could exist, that means that the maximum number is greater than 0. If we say that 0 of this technology could exist, then that just basically means that it can't exist in the solution. And so that's the kind of the point that I'm looking at as I scan down. I'm seeing all of these zeros in that third regular column. And scanning all the way down, so you start seeing some things here. We see the boilers for the central plant. So what I'm going to do is go up to some of the cogeneration equipment. So here we've got reciprocating engines, natural gas engines that take in natural gas and put out electricity, and you can see the efficiencies over here. I realize some of this could be a little uncomfortable right now, but they're all just default numbers. There's no reason to change any of this information unless you have much better information. A lot of research went into developing these default numbers, and they shouldn't change significantly by area. Even the only thing that you might change would be costs, if you wanted to, say, increase these costs by an area cost factor or something like that. But all of these should be much less cost dependent, or the cost numbers shouldn't be as dependent as something like the decentralized equipment. These are relatively big pieces of equipment. Their cost should be relatively stable. It would just be the installation costs for one region over another. So what we're going to do is change these from 0 meaning they can't be included in the solution, and I'll bring them up to some reasonable value. It doesn't matter too much as long as you're not limiting it. I'll go up to 9 for each one just to make sure we've got plenty. Here, these reciprocating engines are just going to produce electricity, and you won't be able to use the waste heat, but they cost less. So it's really a technology that you could put out there if you can open up as many of these technologies as you want to be considered by the optimization as a part of the solution. These are generally not going to be selected when you have the other option if you could use the waste heat. But if you had a requirement to produce electricity, and say your natural gas rate is really high and you don't have much of a heat load, you may actually select something like this to produce electricity when needed, but maintain the lowest possible cost because it's not cost effective to make use of waste heat, something like that. So the technologies are in here, and they may not get used often, but at least we've got a wide breadth of technologies to consider in any given solution. Natural gas turbines are a similar type of technology in that they generate electricity and you can recover waste heat. So we've got kind of both scenarios here as well, where you would just use them for the electricity, or this lower group here, kind of starting at this level, where you could use the waste heat as well. And basically that's just going to have to do with the extra costs for heat exchangers and the additional equipment that would be needed there. And that's added on to the installation cost. You'll see that there's a premium for these other pieces of equipment. Generally speaking, I think if you work in this area, you end up hearing about this a fair amount. Natural gas turbines are usually considered a larger technology, like a physically for a larger electric demand. So there's the sizes in general, you'll see up to 45, this would be 45 megawatt here, where the highest size we've got here for this engine. Larger ones do exist, but up to 5 megawatts. The scale of the technology, you would normally use reciprocating engines for a lower scale of electricity production, and turbines you would use for a larger scale. It turns out that most of our installations, if you're trying to match up with the heating demand at all, which is usually the most cost-effective way to size these things, the scale is much closer to that of reciprocating engines. I haven't found a location yet where natural gas turbines were going to be a great solution, and it's primarily based on that scale. We just don't have that dense of development for most of our installations in general, because land hasn't been nearly as critical to force us into very tight development that way. And so I'm going to allow them as well, but I wouldn't expect turbines to be part of the solution for this group. And then there are other technologies. There's lots of things. Absorption chillers here. If we had a cooling load that we could meet with a chilled water network, I would allow these. As it is, there's really no need to even say turn them on, because there's no way for that chilling energy to be used by the buildings. There's no network present to move it along. And then some other, again, electric chillers. There's no need for any of that. We do have some other technologies here. Usually you'd have a little bit more information when you're putting in something like biomass. We look at how much is available locally, but those technologies are here as well with some approximate costs. That comes from NREL data. They give kind of distributions for every year, every relatively short time frame, they put out kind of a distribution of costs. And so we've got that information in here as well. But those are all the technologies I'm going to include right now, just the main cogeneration technologies. And we'll go ahead and close this larger window and save it. So I explained a fair amount in that process, but you can see that if you were just turning those on, it wouldn't take you very much time. This would be a pretty quick process. Now that we've made a change here, we'll see that the results will gray out, because now we have another study here, not a study, I should say, just a single run that needs to be optimized. Just this one centralized building. We didn't change anything with the decentralized option, so it's just this one right here. We're going to go ahead and click optimize. And while that's going, we can add in the information to do a PV study and add that additional alternative as well. So the first thing we're going to do when looking at PV, this should still only take a minute, but we'll go ahead and make use of our time. The first thing we're going to need to do is go to PV watts. This is a tool that's put out by NREL. I think a fair number of people are familiar with this tool. We go here, it pops right up, PV watt calculator. And this is going to give us hourly data for what a system would output, what a PV system would output of a given size. So we can enter in a location. Let's go with Champaign to be kind of in line with our study. And we can select the weather file. So we'll go ahead with the one they've selected. All right, and I'm going to change the DC system size to 1 kilowatt. All of the energy numbers that they develop, I've gone through and checked this a number of times, they all scale linearly with the system size. So we're just going to model we're going to have PV Watts model a system at a 1 kilowatt size, and then back in, I guess, the under the hood with the NZP tool, we scale it up and down from there. And then we separately handle the costs, which don't scale linearly. As we know, there's some economies of scale. But the results for the energy output are going to scale linearly from this, based on just multiplying up from a certain system size. All right, and then some of the rest of this information we actually don't need to change. A lot of these are standard defaults for their calculator. They give you some additional information. This is just for some background. You can change from residential to commercial. Some of these things, they only affect pricing. They're going to give you some pricing information, and you can change out some of this, but we're not really interested in any of that. We just want the hourly output from this system. So we only changed the one number up at the top, changing from the default of 4 kilowatts down to 1 kilowatt. And here they give us some results, some of the energy output results. But what we really want to do is download the hourly results. So let's save this. I'm going to put it in my temp file here. I'm going to say PV Watts hourly course study. All right, it's completed. Let's open up the folder and we'll open up the file. Okay, so here we have the output that comes out of the PV Watts system. So we've got a whole bunch of columns here, wind speed, angles and different information, irradiance amounts, but all we really want is this last column. This is the AC system output in watts. And so what we want it, we're going to upload it in kilowatts. So we're going to take this and divide by 1,000 and extend that all the way down. I'm going to copy this column into a new tab. And what I wanted to do was just paste the values. Okay, so we've got the values here. And I'm going to extend it out. I don't like to have too many extra decimal points. It actually it causes a few hiccups for the optimization. It just slows it down. It wouldn't cause too many problems, but we don't want to slow it down like that. So I try to go just 3 figures is fine. And they just do a summation here, so we're going to get rid of that summation. And this is a little bit of a particular process, but we'll have it recorded, so if we need to replicate, we shouldn't have any trouble doing that. All right, so we've just got one tab now, and we've got a single column of this output data. And I'm going to go ahead and save it. I'm going to give it a different name, just so we can keep that original file. And it's going to be saved as a CSV file. And that's important. That's what the site, the NZP tool, is looking to upload. Another important thing to remember here, this has caused me some confusion before, you have to close this file. You can't upload the file while it's still open, and the site is not going to give you that information. It's just going to, it won't upload successfully. You won't get the little pop-up that we're going to see here in a second if it was open. So we see your file was uploaded successfully. You would just spin for a second and you wouldn't get that little box up if you still had the file open. So just a little note to keep in mind. All right, so we've now uploaded the solar data that the tool is going to be able to use to determine how much power would be output for given system sizes. And I'm going to go ahead and create another alternative based off the best case. We'll say best case with solar, and we could further define what kind of reduction we want to see, and we change that up in the constraints. So usually I would write something like a 30% reduction in source energy. Let's plus this one up. We'll make that our 5th alternative, and maybe we'll even add this 30% source reduction. Okay, and we'll hit continue. Now, at this point, again, that additional scenario that we created, it's just a copy of the best case. We haven't done anything to allow it to actually look at the source energy. But our other study, or our other scenario that we were just looking at, has completed. Let's take a look at the equipment. We're going to look at the cogen. You see we do have a different number of devices. Let's look in here. And we'll see that it did select reciprocating engines with heat recovery. And when I look at the results like this, we see that there's a 3,000 kilowatt or a 3 megawatt unit that was selected, a 1 megawatt unit, and 3 100 kilowatt units. I look at this as a capacity. This is the planning level of what what scale of cogeneration would make sense to put with these loads. So it just sized this equipment. The smallest scale, these 3 100 kilowatt units, these were going to be at a price premium on a per capacity basis when compared to the larger scale equipment, but it was just filling in to kind of optimize based on the heating load that it saw and the electric rates and things like that and the natural gas rate. So this was approximately the size. It doesn't mean that you would buy exactly those pieces of equipment. This is the first level of planning level study. You could always go back and separately either A, work with somebody else to kind of further develop this, or B, just look at some kind of common sense changes to the sizing. You might select a couple 1 megawatt units that you could have in together, or two megawatt units. So you're back up to that 4 megawatt capacity. Something like that might make the most sense as a final design size. But this very quickly gets you very close to the ballpark of where you want to be looking in terms of the scale of generation and how that fits with your cluster. So let's see what impact that had on the final numbers. Look at this summary report. All right, and we've got the cogen solution now that we can compare against the best case. So our investment, actually, we've got, I think a large amount of this is the building investment. So you don't see small deviations in the investment costs that come from the cluster as much. But some of the investment just moved around. I think it moved off of, we'd have to look back at the at that study. Let me see if I can pull that up. So I want to be able to make this point clearly. Try to pull them up at the same time. Many times I'll have two of these, at least two tabs up, so I can pop between two of the tables that kind of tell the complete story together. We'll look at that equipment, and the point I want to make is that I believe what happened is we actually bought less boiler capacity and then replaced some of that with these engines that we were able to meet. Some of that heat was then used for the installation, and because of that, we didn't need to buy as much boiler capacity to meet it. And so we'll look back at those actual sizes. But looking at the total equivalent annual cost, you'll see that it drops again here by a little bit more than $500,000 a year, something like $600,000 a year. And we could break that down. Let's look at a larger view here. We've got our best case and our best case with cogen, and within both of these, again, we have it broken down in these two clusters. So you are not going to see any changes in the decentralized cluster. I just want to point this out as we go through. But you will see some changes to the equivalent annual cost, and that's where the difference comes between the two centralized building clusters. So we're looking at two different alternatives here, two different future potential realities. And the source energy takes another significant drop from this 76 down to about 53,000 megawatt hours per year. So there's a significant change both in the equivalent annual cost and in the total source energy. Now, when we looked back at comparing the two clusters to each other, one thing we'll notice is that the decentralized building cluster is actually a little bit, let's see, I looked at the loads separately and spent a little bit of time on this. The loads themselves are a little bit bigger in the decentralized building cluster, and that's why you end up seeing higher source energy. It's not, at this point, before we have cogeneration, there's not a big benefit to being on a central system in terms of energy. We're not, the boilers that you can get at individual buildings at this point, can be basically just as efficient as the boilers you'd have at a central plant, and they don't have this large distribution system that you would have losses in as well. You do have some maintenance benefits of having all of your larger equipment at a central place, but in terms of energy, you're not getting a lot of benefit there. There is also a benefit on the chilling side. If you've got a chilled water plant and distribution, you can get more expensive, high efficiency equipment at a plant than you would be able to justify at a building. But we don't have that in this situation. We don't have that. We don't have a chilled water network or anything in this study. So here, the differences are primarily just due to the buildings, the size of them, and the loads for the types of buildings that are included. When you move on, though, to the cogen solution, now we see a real benefit to having these buildings grouped together, to having that synergy that can come from having a reciprocating engine and waste heat recovery. So that's the big point I want to be able to make here, and then we're going to go forward and look at this solar solution as well. Let me try to pull up the equipment so I can show that a little bit as well. And okay, so I'm going back to this equipment overview. I'm going to plus out both of these. And we'll scan down. So here we've got, where are the boilers? Central plant boiler, and we've got 30,000, 3 times that 10,000 existing central plant boilers, and then a 2,500 kilowatt capacity central plant boiler. So everything's in the same kilowatt units here. That's not a standard unit for boilers and boiler outputs, but we can convert from those as well. It's just nice to have it all in the same capacity when you're doing or the same units when you're doing calculations on these. Okay, and then similarly here, now we've dropped down to 20,000, 2 times this 10,000 here, and then another 5,000 from the 2 times 250 or 2,500 here. So we've got about 25,000 kilowatts of capacity for heating here, and about 32,500 up here, so that the boiler capacity has dropped down, and that capacity has been replaced to some extent with the reciprocating engines. So that's just to get a better feel for what's happening. I think you'll end up, as you develop these solutions, you'll want to go back and forth and say, okay, I see the cost changed, I saw that the energy changed. What actually happened? Where am I getting that benefit from? What are the sizes for the different pieces of equipment and things like that? All right, let's go ahead and look at the current source energy. This is another thing that I'd usually do before finishing the electric or the solar PV scenario. Many times it's not cost effective to add any solar PV, and so you have to constrain the solution to force that it's more cost effective to buy from the grid. And in many ways that makes sense. If it was generally cheaper without any other incentive to have PV supply electricity, then that's where all of our electricity would come from. That would be, if on an annualized basis, we don't have any issue generally with capital, with getting capital in this country. If it was annualized lower cost, then it would be the preferred method. So because that's not always the case, I usually have to add some constraint. And if I want to get to 30%, then I need to know what the current source energy is. Now, some of the requirements, even though we talk about ESA and some of the executive orders that have come out recently that talk about what percentage they want, 30% number that's often thrown around is usually actually based on the electricity. So it's 30% of the electricity usage. You could base it on anything you want here, but that's usually what the requirement is. So if we wanted to do,
what happens?
Go ahead.
What happens if you go unconstrained? What does happen?
We could do it really quickly here. Maybe we should, just for instruction first. It's going to be different in each place. So let me, depending on the utility rates. So let's close this, and we'll go ahead and try that. So the first thing, we added the PV data. So it's not built into the system to develop or to have the output of what different PV systems would put out, different size PV systems. So we do pull that information from PV watts, and that's what we did a minute ago. And then you'll have to go in here in this scenario and open up that equipment, and that allow it in the solution. So if we hadn't uploaded that data file for the electricity wattage that's going to be provided by these different systems, then they're all just going to show up as zeros. And even if you allowed this equipment, so here are different PV systems, and I'll talk about these sizes in just a minute. Even if you turned these on in this way, allowing them to be selected, they would all show up as zeros. It'd look like you're paying for something and not getting any energy out of it, and that's why we have to download that file, make some adjustments, and add it into this tool. So here I'm going to open it up without putting any additional constraint. And so this just says that these systems could be selected. So if the electric rate is high enough and it makes sense on an annualized basis to select it, then it will. We'll go ahead and save it. I use 9 a lot of times for this maximum number. You can make it as large as you want. There's no concern there. There are some things we just get used to doing. I don't want it to seem like that's part of the process. All right, and worst case scenario, if you found something and it was cost effective and it selected, say, 9 of the largest scale. This is a 1 megawatt system. Here's 100 kilowatt, 1,000 kilowatt, 10 kilowatt. This is on the order of something that maybe a large residential system, and then these are much larger systems. The worst case scenario, it would just select maxing these out. It would buy all of them, and you'd realize, oh, it took as much as I allowed. I could go back and change those, and and get the results with updated numbers in there. So we'll go ahead and optimize this. Again, with that key term, without adding a constraint, if it's not cost effective, they're not going to be selected. We're optimizing it with a constraint that's going to require a certain amount of renewables. If that's the only renewable available, then it will select solar PV, and you'll just get to see what the cost delta is for that scenario. It may still be worthwhile, and I think many installations will want to see what that cost number would be. So this tells us that the solution is done. It's just pulling the results back. You'll find that some of these things the difference in the calculation time is dependent on what you're looking at. Some of the cogen solutions where they've got to choose sizes, it can take a little bit more time, still within a couple minutes. But most of the other ones are pretty quick, closer on the order of seconds. And it looks like we can see here this best case that's unconstrained looks like it has the same number of devices, so I'm not expecting to see any solar PV in here, and we don't end up seeing it. So it wasn't selected, and I think that we would need to constrain the solution for a lower source energy so that PV can offset the source energy and will be selected. So let's say that we want to reduce, if our current best case is at 180,000 megawatt hours per year, let's try to drop it down to even 150. That would be a good reduction that we can show here. Another thing to keep in mind here, this is in kilowatt hours, so we do have to change add 3 zeros there to get up to megawatt hours. That's an easy thing to forget about. So here we're at 150,000 megawatt hours, or 150 million kilowatt hours. I'm going to go ahead and save that. And actually, I only did it for the centralized cluster. Again, you could split this up. Actually, that's, yeah. So let me look back over here. It's a good point. again, I often do this with a single cluster in mind as well. That's the total sum for the two. So what I really need to do is reduce the source energy for a single cluster. So if we wanted to reduce it by 30,000, maybe I can take this one, the decentralized group, down to 70,000 megawatt hours. Did that make sense? Where I was causing, may have caused a little bit of confusion. I was looking at the total number for both clusters, but when we analyze them, we're looking at them as separate clusters. They're just then summed up to this total number. So I'm going to go back in over there, go to the decentralized buildings, and change the source energy to 70,000 megawatt hours. So I would like to just cancel that. This is going to be too large anyway. It doesn't really matter. It's not going to constrain it if it's above the level that it would currently be sitting at. Okay. So this should constrain our decentralized buildings. We'll save that. One more thing to keep in mind, I believe when I made the changes, I only saved adding the PV onto the centralized cluster. And now that I'm putting the constraint on the decentralized side, looks like I put a period in here as well. I'll need to make sure that that's available on the decentralized side. Now you could do some on both sides. That's not an issue. You could do a certain amount of capacity on, to further reduce the scale or the source energy on spread among your clusters, no matter how many clusters you have, how many different building groups. I'll actually make the lower one. Many times I'll do 9 for these smaller scale systems because if they got to 10, I guess this is the logic for it. If it gets to 10, then it would just select the next 10 times larger system because it's more cost effective. And then if I'm working with a very large cluster, I might make the last one much bigger because it doesn't have anywhere else to go. It has to be fully taken care of with that final large size. I don't think we'll actually get up to that scale, but I didn't run through the numbers separately, so we'll go ahead and make that a larger number. Okay, and since I was talking while I was doing it, after it saved, it went back to the centralized, so it looks like I did that on the centralized one. I'm going to make sure that I do it on the decentralized one. And it doesn't matter, I'm going to leave the solar option open on the centralized buildings. Since they're not going to be constrained and it's not cost effective, it's not going to make any difference anyway. Okay, so we'll go to the constraints next and back over here. Okay, so this should be all set. We've already entered this in. We're going to go ahead and click optimize. And it should take just a few seconds to run while it's doing that. I'm going to go back over here to alternatives. Okay, so this should be done soon. You can see that they're running right now. And the centralized buildings scenario is only running because I changed the equipment there as well. That was accidental. We shouldn't see any changes there. Okay, so everything's done. We're just waiting for it to populate into the interface so we can take a look. Okay, so I'm looking first at the centralized buildings just to make sure there weren't any surprises. I don't see any solar here. Solar was allowed. We opened it up so that those solutions or that technology was allowed, but because it wasn't cost effective, it wasn't selected. And if we look down to the decentralized buildings, we see 7 megawatts of capacity for this system, 7 times this 1 megawatt system. and then 300 kilowatt, and down to 10 kilowatt. So these systems again are going to be slightly less cost effective, but the bulk of the cost in terms of economies of scale and everything, it's the same idea in that you wouldn't buy these exact system sizes, but this scale of solar is what would be required to meet that requirement. To meet that, I think it was 30,000 megawatt hour reduction per year requirement. So that's the way that, again, just a way to interpret those results. Let's go back over to decision analysis and reports. And this can be a good way to compare the different technologies as well, having these two different scenarios. All right, let's blow this up to look at it all together. Looking at the total site energy, or total source energy. Here we see a drop from the base case, or the best case, down for the cogen, and because of the level that I selected, that 30,000 reduction in source energy, an even further reduction here for the best case with solar, but the cost goes up significantly, over $1 million a year more expensive to use that solution. So we could even potentially look at reducing the amount of solar that was selected so they lined up, and you could see the cost of reducing source energy between those two technologies. There are other ways that we could do this, but generally this says we could reduce source energy much more cost effectively first by doing this cogen, by adding an engine to the centralized cluster, making use of that waste heat. And then if we needed to go further, maybe our next solution would be looking at solar. It's not as cost effective, but it can still push us further. Those decentralized buildings, we don't have the same options. We don't have a lot of potential. We could look at putting them on a central network, or look at including them on the existing network, extending the network and doing things like that. It gets more, that gets more complicated. I think we'd have to spend a little bit more time talking about what that would take. But generally, the flexibility you get with the central network is the ability to add these other technologies at a single location, larger scale technologies. So these are some of the really powerful things that we can do and show the customer, show the client what what future scenarios might look like and what their energy and cost implications would be, both on an absolute cost basis and then also on an annualized basis, to find that lowest life cycle cost point.